So this would be the next lecture on rotational motion from the book of Irodov. Okay, that chapter is there given as dynamics of a solid body. So there are almost 10 to 12 questions left from the chapter of rotational motion. Otherwise, the entire chapter is complete. Okay, and one thing I don't know if you have realized it or not, but I'm not cherry picking any questions. Okay, I'm giving you the entire solution. The purpose of that is what can I say? See, one thing you have to understand for advance. Okay, uh, see, even concepts that are not inside your syllabus. Okay, but the fundamental of that concept is inside your syllabus. That question or those concepts or that questions can be molded or simplified into your questions. Okay, and advanced question have repeatedly done that again and again. Okay, the questions that are outside your syllabus, they have been molded such that the core concept is inside your syllabus, and they're given the question straightforward. Okay, so it's not entirely harmful to learn those questions. Okay, and few topics such as relativistic mechanics and those are completely out of syllabus, that has no connection with the basics or fundamentals with your syllabus, so I'm skipping entirely that. The purpose of giving each and every question is not to show off or thing kind of thing. The purpose is that you do not skip any kind of thing that can be molded into a question. Okay, so without any wasting any further time, let's move on to our next question. Question number 1.273. Okay, and in this question, a uniform rod of mass m 5 kg and length l 90 centimeters, it's on a smooth horizontal surface. Okay, one end of the rod is struck with an impulse of 3 Newton per second in horizontal direction, perpendicular to the rod. As the result, the rod obtains a momentum of P is equals to 3 Newtons per second. Acha. See, if impulse is given as 3 Newtons per second, the change in momentum will also be 3.3 Newtons per second only, no? Not per second, 3 Newtons per second. So this is kind of a redundant information. That means we do not need kind of implicit information. Okay, either this or this. Both explains the same thing. Find the force with which one of the rod will act on the other in the process of motion. This is our question. So what this question is basically saying is that suppose there is a rod out here. Okay, this rod, and there is a ball out here. Let's say any mass. Okay, the mass of this ball is not important, but the process of striking means this ball strikes this rod with some velocity, and after that it gives an impulse to this rod. Okay, and this rod starts moving and rotating simultaneously. Okay, the impulse is given as 3 newtons per second. Okay, we have to find out the force exerted on the midpoint of the rod. That means what? Imagine this rod. Okay, imagine this rod to be rotating like this. Okay, it is rotating like this. This counterclockwise direction. Okay. Now each element out here, each incremental element out here experiences a centrifugal force. Okay, centrifugal force. That means what is keeping this rod together? The tension force by the material, isn't it? Suppose if this rod was made up of very paper something. Okay, suppose this rod was made of paper. If it would rotate very fast, it would tear itself apart, no? Okay, so we have to find out the net force at the center. And how do I do that? Let's say the impulse is given as 3 Newton per second square. Okay, now I'm considering this center, and this entire top half of the portion of the body is considered as a point mass. Okay, and the bottom half of the body is considered as a point mass. Okay, so if m is the mass of entire part of the body, what is the mass of the top half? M by 2. And fine, the mass of the bottom is also m by 2. Now, where is center of mass of the top half situated? If the entire length is L, okay, this is the entire length of the rod L. How much is this much length? L by 2. And where is the center of mass of this L by 2? Out here, half of this length, isn't it? So the position of the center of mass meaning this position, m by 2. Okay, m by 2 is located at L by 4 from the center. So the top half portion of the body is located at L by 4 from the center. Similar kind of situation for the bottom half. This m by 2 is also located at L by 4 from the center. Understood? And now this is rotating with angular velocity omega. Okay, and we have to find out the centripetal force at the center. Understood my question? Okay, and once you have understood the question, now the approach is very straightforward. Okay, now we know that linear impulse is equal to change in momentum. So angular impulse would be change in angular momentum, no? Fair and fine. Okay. Now suppose this ball of any mass struck out here, okay, with same momentum p. Let's suppose the momentum of this ball was j as given in the question. And while striking this body, it transferred its entire momentum to this body. Okay. And this body now has a momentum 3 newtons per second. What is the angular momentum? We already know that angular momentum is equals to r cross p, isn't it? Okay. So where is my center or where is my origin? The origin would be considered at the center. Okay. If I take my frame of reference from the center of the rod, that means I would see it as pure rotation, isn't it? Okay. And what is the value of r? The value of r is nothing but, I have already shown you in class. Doesn't matter if a body is moving in a straight line. Okay. The angular momentum at every point will be nothing but this much length. Why? R or this r into sine theta is nothing but this much length. And this much length is nothing but L by 2. So r sine theta is always L by 2. And I've showed this repeatedly in class. Okay. So what is the value of angular momentum? The value of angular momentum is nothing but L by 2 into J, that is given in the question. The linear momentum out here is written as J. Okay. So angular momentum L is equals to L by 2 into J. Understood? Now the question becomes very simple. Angular momentum is given by I into omega. And once I find out the omega out here, I can easily find out the centripetal force. Centripetal force is nothing but m omega square r. Okay. So all I'm left to do is finding out the value of omega. Understood? So L by 2j is equals to I into omega. What is the moment of inertia of the rod? Okay. Okay. Let me blur out myself a little bit more. Okay. Moment of inertia of the rod to the center is nothing but ml square by 12. If the mass of the rod is ml square by 12. And by this formula, I find out the omega. So what is the omega? Omega is nothing but L by 2j into 12 by ml square. Okay. L and L square would get cancelled. So omega is equals to 6j by ml. 2 and 12 would get cancelled to become 6. Fair and fine. Once I find out the value of omega, centripetal force at the center, okay, is nothing but m omega square. What is the mass of one half of the rod? If the entire mass of the rod is m, the mass of one half of the rod is nothing but m by 2. So m by 2. What is the value of omega? This one. Centripetal force is nothing but m omega square r, no? So omega is nothing but this one. 6j by ml square into what is the value of r? The value of r is nothing but the center of mass, or what I have taken the entire mass to be concentrated, okay, which is at L by 4 into L by 4. And this is, if I simplify this would be our answer. Okay, let's simplify, just simplify this. Fc is equals to m by 2 into 36 j square divided by m square L square into L by 4. Okay, L and L will get cancelled, m and m square will get cancelled. 2 and 36, 80. Centripetal force due to one half on the other half is nothing but 18 j square divided by 4 ml. What came out? 29. Centripetal force is equals to 9 by 2 j square by ml. Understood? So this is our first question of 273. Now we'll proceed with the next question. Okay. So let me dim myself a little bit. So in this question, a thin uniform square plate with side L and mass m can rotate freely about a stationary vertical axis coinciding with one of its sides. That means what is happening out here is there is one axis of rotation. Okay. And there is a square plate out here of mass m and side L. That means this side is L and this is mass m. And this is rotating about this axis with angular velocity omega. Okay. If one of these sides, if a small ball of mass m flying with velocity v at right angle strikes a placed elastically at the center of it, that means what is happening is, see, this was the hinge, and this rod, okay, this rod was rotating like this, isn't it? Okay, I'm showing the same diagram but in this manner. Okay, this same diagram I have rotated it like this. Understood? So what will happen is, out here there is a hinge, okay, and this is the rectangular slab of mass m. Now what the question is saying, if there is a small ball of mass m flying with velocity v, okay, towards it and strike to the center of it. Center of it meaning, if this is distance L, the ball will strike exactly at L by 2 from the axis. Okay. The question is asking what is the velocity of the ball after impact. So let's say this is before collision. Before collision. Okay. After collision, what would happen is, see, this block, this is the rectangular plate of mass m. Okay, this is start moving with angular velocity omega, no? Okay, and this block will move already equal with some other velocity v dash. Okay, now my first question is, if I want to find out the value of v dash, what should be my equations? Okay, this is the situation before collision, this is after collision. After collision. Okay, my first question is, what are the equations that I can make? First one is coefficient of restitution. Okay, so coefficient of restitution. Restitution. Okay, coefficient of restitution. First part. The second equation will come from conservation of angular momentum. Conservation of angular momentum. Okay. Now, how do I apply these equations? First one is simple. Coefficient of restitution. What does coefficient of restitution say? Velocity of separation is equal to velocity of approach. Or coefficient of restitution is nothing but velocity of separation. What is the velocity of separation? See, the midpoint of this slab or the midpoint of this square slab. With what velocity is the midpoint of this square slab moving in this direction? It is nothing but omega into L by 2. This point, the midpoint, will move with omega into L by 2, no? In this direction. So what is the velocity of separation? Omega L by 2 plus v dash. Why have I shown v dash? See, if this direction is positive and this direction is negative, always consider direction while dealing with vectors. Okay. So velocity of separation is nothing but velocity of one body minus velocity of the other body. So omega L by 2 minus of minus v dash is nothing but omega L by 2 plus v dash. So this is the velocity of separation divided by velocity of approach. What is the velocity of approach? V. V. And what is the coefficient of restitution for elastic collision? 1. How do I know it is elastic collision? It is given in the question. Look. Okay. Elastically. Understood? So, and my second equation. My second equation is nothing but conservation of angular momentum. How do I conserve angular momentum in these two scenarios? First one. What is the angular momentum of this mass m moving in a straight line about this inch? About this inch. Okay. This is nothing but m into v into r sine theta would be nothing but L by 2 because this is striking at the center. No? Understood? So conservation of angular momentum is nothing but mvl by 2, mvl by 2 plus angular velocity of the plate is nothing but 0 plus final angular momentum plus final angular momentum is equals to final angular momentum. Final angular momentum is nothing but I into omega. I omega minus out here why minus because this momentum is in negative direction minus m v dash okay into L by 2. You cannot forget the L by 2 out here. Understood this much? So this is my equation 1. This is my equation 2. Okay. So solving this equation, I have to find out the value of v dash. How do I find out the value of v dash? See, what is the redundant variable out here? The variable that is not needed. Omega. So somehow I have to isolate the omega from this equation and isolate the value of omega from this equation. And if I equate this to omega, the term omega will disappear from the combined equation. Understood this much? Okay. So let's isolate the value of omega. V is equals to omega L by 2 plus v dash. Okay. And v minus v dash is equals to omega L by 2 and 2 by L. V minus v dash is equals to omega. From this equation, before substituting this equation, what is the value of I? Or what is the value of moment of inertia of the square plate about this axis? This is nothing but ml squared by 3. Okay. So this is capital ml square by 3. So mvl is equals to ml square by 3 minus mv dash L by 2. Okay. And out here, what do I have to isolate? I forgot the omega out here. So I have to isolate this value of omega. So let's take term mvl plus mv dash L by 2 is equals to ml square by 3 omega. This would be nothing but how much? Okay, 3 by m L square into m v dash mvl plus m v dash L by 2 is equals to omega. Okay, how do I deal with this? Okay, let's cancel out L and L square out here. Okay, I'm simplifying from the start only. No need to complicate it further down the line. Okay, so I'm taking m common outside. Okay, so it is nothing but v plus v dash by 2. This entire equation would be nothing but v plus v dash by 2. V plus v dash by 2 is nothing but 2v plus v dash by 2. So 2v plus v dash divided by 2. And these two would go outward. Okay, these two would go outward. Okay, and fair and fine. Now I just have to equate this omega and this omega. So I'll simply get 2 by L v minus v dash is equals to 3m by 2 ml into 2v plus v dash is equals to omega. Okay, what do I have to find out? I have to find out the value of v dash. So now let's take all the term of v dash to the one hand side and all the other terms to the other hand side. So 2l by v minus 2l by v dash is equals to 3m by 2 capital ml into 2v plus 3m by 2 capital ml into l into v dash. Okay, okay, or I'm just taking this v dash term to the right hand side and bringing this term to the left hand side. So 2 by lv minus 3m by 2 ml into 2v is equals to 3m by 2 capital ml v dash plus 2 by l v dash. Okay, or 2 okay, 2 by lv minus 3m by ml into v is equals to v dash into 3m by 2 ml plus 2 by l. Okay, let's cancel out the l and this out. I do not need the l. Okay, so v dash is nothing but 2v minus 3mv by m divided by 3m by 2 capital M plus 2. Okay, and if I take this v common, okay, what will happen? Is equals to v dash. So if you simplify this, you will get your answer. Okay, fair and fine. I'm not further simplifying it. It will be nothing but 2m minus 3 small m, and denominator will be 3m plus 4 capital M, and m and m will get cancelled from the denominator. You understood this? Okay. So this is first part of the question. Calculate the value of v dash. The second part of the question. Okay. The second part of the question is asking, find out the horizontal component of resultant force which the axis will exert on the plate after the impact. So what is the horizontal component of force? See, this plate will rotate with angular velocity omega, no? So in the previous question we have done, there is a centripetal force exerted by the center. Because this body is moving in circular motion, or the center of mass of this body is moving in circular motion, there is something necessary to keep this body in circular path, no? And that is nothing but the centripetal force. And the centripetal force exerted by this hinge, okay, by this hinge out here, is nothing but m omega square r. Okay, so centripetal force is nothing but m omega square r. I very much understand that. So part B of the question, centripetal force is equals to m omega square r. Now lies the trouble. What is the value of m? Mass of the block or mass of the rectangular slab. What is the value of r? The value of r is nothing but the center of mass of the rectangular slab. That means I've considered this entire rectangular slab to be a point mass, and that is moving with angular velocity omega, or that is rotating with angular velocity omega. Okay, the center of mass would be nothing but L by 2. See, L by 2 from the axis, if you cannot see it. Okay, so these two parts are simple. R is nothing but L by 2. Problem is, how do I find out the value of omega out here? The same approach. Same approach means, see, these are the two equations that I got, no? This was the first one, what is the first equation? This one was the first equation, and this one was the second equation. Okay, these two are the equations that I got from coefficient of restriction and conservation of angular momentum. First, what I did, I will eliminate the value of omega to find out the value of v dash. Now I don't need the value of v dash. I need to find out the value of omega out here. So the redundant variable in this two equation is nothing but the v dash out here. So some have to combine this equation and eliminate the variable of v dash. How do I do this? Same process. Isolate v dash, combine the v dash, or equate the v dash. Okay. So I'll copy these two equations. Let me copy the two equations. Okay. So copy, paste. So Okay, just copy it out. Okay, and okay, here's my equation. I cannot lose this equation. Okay, so this is my equation. The same two equation. Instead of isolating the variable of, what do I call that, v dash, and to isolate the variable of omega, I need to find out the value of omega. So isolate v dash. Why? Because v dash needs to be eliminated. V is equals to omega L by 2 plus v dash. Okay. So v minus, what is v? V minus omega L by 2 is equals to v dash. Okay. And this is nothing but mvl by 2 is equals to, okay, ml square by 2, sorry, ml square by 3 into omega minus mv dash into L by 2. Now if I take this, I have to isolate the value of v dash. So m v dash L by 2 is equals to m L square by 3 omega minus mv L by 2. Okay. So v dash is nothing but 2 by ml. 2 by ml into m L square by 3 omega minus 2 by ml mv L by 2. Okay. So this is my simplified equation. So let me just cancel out whatever is cancelable. L square and this will get cancelled. So let's cancel this out. Okay. 2 out here and 2 out here would get cancelled. M out here and M out here would get cancelled. L out here and L out here would get cancelled. Okay. Let's cancel this. What we're left with is nothing but V. So if I write this equation neat and clean, minus V. Understood? So V dash is nothing but 2 by ml by 3 omega minus V. Now what I need to do is I need to equate this V dash and this V dash. So V minus omega L by 2 is equals to 2 by ml by 3 omega minus V. Isolate the value of omega on one side and V on another side. Okay. So V plus V. If this V goes to the left, it becomes 2V. 2V is equals to 2 by ml by 3 into omega plus omega L by 2. Okay. If I take omega common, it will be nothing but 2V is equals to 2 by ml by 3 plus L by 2. Okay. And this will be nothing but omega. So omega is equals to how much? So omega should be equals to 2V by 2 by ml by 3 plus L by 2. Now I can simplify this one, but the crux of omega will be this one. Okay. Now this value of omega I need to substitute out here, and that would give us our centripetal force. A centripetal force Fc is equals to m into 2V by 2m into ml by 3 plus L by 2 square into R. What is the value of R? The value of R is nothing but L by 2 into L by 2. So this is my answer. I'm not further breaking it down. Okay. So you can simplify this one. Simplify this one means just simplify the variables. Okay. There's no calculation of further. There's no any further equation to be done. Okay. Understood? So this was the question. Simple enough. So this question is nothing but those question of HCV that you do. Okay. In mass of rod L is a rod of mass M is there and a ball strikes it with some velocity V. And have to find out the maximum angle it tilts. Okay. So how do you do this kind of question? So we apply conservation of momentum before and after collision, and after that we apply work energy theorem from this point to this point. So simply we'll do the same thing out here. Okay. So there is this rod L. Okay. So suppose there is a rod. This is the hinge, and this is the rod. Okay. Of mass M and length L. Okay. Out here we assume that small mass M, okay, a small ball of mass M is moving with velocity V, okay, and is colliding with this rod. And let's say this is before collision. Before collision. Before collision, what would happen is the ball would simply go. The rod is initial static out here. And let's say after collision, what happens is after collision, this is the same rod. Okay. the ball gets stuck out here, m, and starts moving with angular velocity omega. Okay, this is after collision. Okay, so before collision and after collision, what can I find out? What can I apply? I can apply conservation of momentum or conservation of angular momentum. Okay, just before and after collision. Okay, and after collision, what is happening is this rod moved by a hinge like this. Okay, by an angle alpha. The ball is stuck out here. Okay, in elastic collision. Okay, now between these 2 points, I'll apply work energy theorem, and between these 2 points, I'll apply conservation of angular momentum. Okay, so let's apply conservation of angular momentum. Conservation of angular momentum. So in applying conservation of angular momentum, let's see. Okay. So after we apply conservation of angular momentum, okay, let's see. So initial angular momentum. What is the angular momentum of this point mass moving in a straight line about this point or about the hinge? Is nothing but m into v into l. Okay. So initial angular momentum is nothing but mvl. What is the final angular momentum when both the mass of capital M and the ball of small m starts moving with angular velocity? I total into omega. So I total into omega. What is the value of I total? So mvl is equals to I total is nothing but moment of inertia of the rod about this hinge is nothing but ml square by 3 plus moment of inertia of this point mass about this hinge is nothing but ml square. Okay, ml square into omega. Okay, now in the question you have to ignore the value of small m, but I'll do it later. Okay, so I'm not taking that assumption into account. I'll do it much later. The second part of the equation is nothing but between these 2 points. Between these 2 points, what can I apply? Conservation of kinetic energy, not conservation of kinetic energy. Kinetic energy won't be conserved. Why? Because gravity force is doing some kind of work. See, initial kinetic energy, finally it will come to a test, no? So I can apply work energy theorem. Work energy theorem. What does work energy theorem says? Say, change in kinetic energy of a body is equal to work done by all the forces. Okay. So if I apply work energy theorem out here, what is the final kinetic energy after it has moved by an angle alpha? 0, because after it moves by an angle alpha, it would again try to come down, no? So before coming down, the final angular velocity at maximum height is nothing but 0. So final kinetic energy at maximum height is nothing but 0. Minus what is the initial angular velocity? Sorry, initial kinetic energy, half I omega square is equals to what is the work done by gravity force? The work done by gravity force is nothing but exactly how much has the rod moved up by, or how much the center of mass of the rod has moved up. The center of mass of the rod has moved up by nothing but mg into L by 2. L by 2 is the initial position of center of mass of the rod, and final position of center of mass of the rod, or vertical component of position of center of mass is nothing but L by 2 cos alpha. So mg L by 2 minus L by 2 cos alpha. Okay, and the work done by gravity force, since the center of mass is moving up, work done by gravity force is negative. So I'll just eliminate this half I. What is the value of I? The value of I is nothing but ml square by 3 plus m into L square into omega square is equals to mg L by 2 into 1 minus cos alpha. Achha, one more thing. If this rod, okay, if this mass m is also moving upward, no? Isn't it? So I have done only work done by gravity force on the rod. So what is the work done by gravity force on the this small mass m? Is nothing but m into L minus L cos alpha. Isn't it? If I take L common, it will be nothing but m into L 1 minus cos alpha. M into L 1 minus cos alpha. And if I take minus common from left and right hand side, this m will become, or this minus sign will become positive. Understood? And let me even take common out here. Let me take L by 2 common out here. Okay. mg L by 2 1 minus cos alpha. So these are the 2 equations that I get. This is the first equation, this is the second equation. What do I need to find out? I need to find out the value of v. What is the dependent variable out here? Omega. So somehow I have to isolate omega out here, and equate the both. Then I'll get the value of v. An equation with value of v. Okay. So plus ml into 1 minus cos alpha. Okay. So somehow if I isolate the value of v, what do I get? I'll get omega is equals to out here. Omega is equals to mvl divided by ml square by 3 plus ml square. Okay, if I take L square common, I'm taking L square common and moving it out. Okay, L square. I can cancel out this L and this square. So I will get nothing but this value. Okay, if I take ml square out here, this there would be ml square by 3 plus r. I've taken m by 3 this value. Okay, so omega is nothing but this value. Out here, what is the value of omega? Let's do the same thing. Out here, I'll take L square common. Okay, so I'll take L square common. Okay, I'll cut out this one of the square with L and L. Okay, so I'll get something like omega square is equals to mg by 2, mg by 2 plus m. Out here also g is missing. Out here also g was there. mgh, mg into 1 minus cos alpha into 1 minus cos alpha divided by this entire term shifted to bottom of here. So L by 2 into m by 3 plus m by 3 plus m. Understood? So this is our equation. Okay. So if I equate omega from both hand side, I'll take omega out here, substitute out here. So omega square or this entire term square is equal to this entire term. So mv by m by 3 plus m into L, okay, whole square is equals to mg by 2 plus mg into 1 minus cos alpha, 1 minus cos alpha divided by L by 2 m by 3 plus m. Okay, now let's simplify it. How do I simplify it? M square v square divided by m by 3 plus m into whole square into L square is equals to m. Let me take g also common out here. Okay, so m by 2 plus m into g into 1 minus cos alpha, okay, divided by L by 2 m by 3 plus small m. Okay, out here L square and L would get cancelled. Okay, and this m by 3 m and this entire thing would get cancelled. So this 1 by 2 remaining out here, I'll take this 1 by 2 to the top hand side. Okay, into 2. Okay, fine, fair. What do I need to isolate? I need to isolate the value of v square. Okay, so I'll get nothing but this is not square, this is 2. Okay, so v square is nothing but m by 2 plus m into g into 2g, okay, into 1 minus cos alpha. This 2 is written out here. We don't get conflict of them. Okay, and what do? I take this entire term to the left hand side. Okay, okay. So m by 3 plus m into L. Okay, and since I already found out the value of v square is nothing but this much term. Why is mine? V square is nothing but this one. So v would be nothing but under root of this entire term. Okay, now you can take the assumption that small m is very much larger than capital M. Sorry, small m is very much smaller than capital M. So wherever m is there, okay, in plus term, you can ignore that. Okay, so you'll get something around v is equals to under root 2g m by 2, okay, into 1 minus cos alpha plus m by 3 into L. And if I simplify this, I'll get something around v is equals to under root of how much? 2g, okay, 2gl into m square by 6. 2gl into m square by 6. Okay, okay. Is it m square by 6? Yeah, m square by 6. Okay, and how much? M square by 6 into L. M square by 6 into 1 minus cos alpha. 1 minus cos alpha. This is somewhat dimensionally incorrect. Okay, so let me figure out what I have made the calculation a little bit wrong. Found it out. Look out at this m square. I have completely forgotten about this m square, isn't it? So you cannot do that kind of mistakes out here. Okay, so I cannot do that kind of mistakes out here. So this m square will come down out here. So this entire term would be divided by m square by m square. M square is inside the bracket. Okay, m square inside the bracket. Inside the bracket is m square. Okay, and it would be m square. Now the question is dimensionally correct, and this is the value of v. The second part of the question: what causes the change of that momentum? This is a very theoretical question. Change in momentum is caused due to the interaction of force. Okay, so elastic collision is there. Inelastic collision is there somewhere in between elastic and inelastic collision, where coefficient of restitution goes from 0 to 1. So if you want to understand that theory, it's better if you go through the book of Wesley and Hilligan. Okay, it's really explained in very detailed manner. That part. Okay. Now the third part of the question: at what distance x from the upper end of the rod the bullet must strike for the momentum of the system bullet rod to remain constant during the impact? So let's see the third part of the question, part C. Okay. So suppose the same system was out there. Okay. This was the same system. Okay. Now this is hinge. This is the rod. Okay, of mass m, and this was static. Now the ball of mass m is not striking at the end; it's striking somewhere at B2. Okay, at distance x. Understood this much? And after it strikes the combined rod plus ball system, okay, the ball gets attached to the rod, okay, and the combined system moves with angular velocity omega. I need to find out the velocity. The velocity is given same as that. Okay, I need to find out the distance x such that initial momentum and final momentum, okay, is same. Understood? So initial angular momentum and final angular momentum is also same. Initial linear momentum just before collision and final linear momentum just after collision is also same. So I have to apply two equations out here. First one is conservation of angular momentum. Conservation of angular momentum. Okay. Conservation of angular momentum simply, I have done this before. Okay, little bit up. And conservation of linear momentum. Conservation of linear momentum. If I do these two equations, I'll get my value of x. How? Let me make the equation. Conservation of angular momentum. Initial angular momentum is nothing but m into v into x. Initial angular momentum of the hinge, m vx, is equals to final angular momentum, I into omega. I is nothing but ml square by 3 plus m into x square into omega. Okay, final angular momentum. This is the final angular momentum. Conservation of linear momentum. Initial linear momentum is equals to mv, m into v. What is the final linear momentum? With what velocity is this mass? What linear velocity is this mass moving? M small m into omega into x, isn't it? So mv is equals to m omega x plus what linear velocity is the center of this rod or center of mass of this rod moving? M L by 2. M L by 2. Okay, into omega. Understood? Now, if I solve these two equations, I need to find out the value of x. Okay, how do I need to find out the value of x? What is the redundant variable out here? Omega. So somehow I need to isolate omega, somehow I need to isolate omega. Okay, after isolating omega, I'll get a combined equation. Out in that combined equation, I need to find out the value of x. So simply do it. Omega is equals to mvx divided by ml square by 3 plus m into x square. In this equation, what will happen? If I take omega common, mv divided by mx plus ml by 2 is equals to omega. Okay. Now somehow I need to equate these two omegas. So if I equate these two omegas, I'll get nothing but mvx. So mvx divided by ml square by 3 plus m into x square, okay, is equals to m into v divided by mx plus ml by 2. Okay, and what can I cancel? Mv mv would get cancelled. This will become 1. Okay, if I can take nothing common, no? So let's isolate. Cross multiply and isolate. So mx square plus ml by 2x is equals to ml square by 3 plus mx square. Okay, and this mx square and this mx square would get cancelled. So I'll get ml by x. M and m will get cancelled. L square and this would get cancelled. So x is equals to 12 by 3. Understood? So this is our question. Okay. So now we move on to our next question. Okay. So to first understand the question, let me. In this question, there is a disk out here. Okay. So there is a disk. Okay. And this is the axis of the disk. This is the axis of the disk. Okay. And inside this disk, there is a groove kept out here. Groove meaning a slot. Okay. And in this slot, there is a ball out here of mass m. The mass of the disk is capital M. The mass of the ball is small m. Okay. And this ball is connected by a rope, and at the center of disk there is a hole, and someone is pulling this rope by a thread that is passing through the center of this disk. Okay, so if I view the same disk from top, that means if I'm observing this from top like this, okay, how will my diagram look like? This was a disk, okay, of mass m, and this was the slot. Out here there is a ball of mass m, and there is a rope connected to this ball. Okay, there is a rope connected to this ball that is being pulled through the center. Okay, and if I look the same disk to this flat plate or from to the front. Okay, I'm looking this disk from the front like this. So this would be a circular disk. This would be a circular disk, okay, of mass m. This is rotating about this axis, okay, in this direction. This is rotating about this axis in this direction, omega. This disk is rotating about this axis in this direction, omega. These are the three different views of the same thing. Okay, so out here there is a small ball of mass m, okay, and attached to this ball is a rope, and this rope goes through the inside of the disk, and someone is pulling it down out here. Understood? So this is our setup. Okay, so let me draw the rope. This is the rope that is being passed to the center of the disk, and someone is pulling it out here. Understood the setup of the question. Now the question is asking, when I pull this thread, this ball went to the center of the disk. Okay, so what the first question is asking, what is the angular velocity of the system in its final state? That means initially the whole system was moving with angular velocity omega naught. Okay? Initially the whole system was moving with angular velocity omega naught. Omega naught. Omega naught. And when this ball is the center, what would be the angular velocity? Okay. The second part of the question is asking the work performed by the force. So let us analyze the process, or what should be the workaround for this problem. See, can I apply conservation of angular momentum for the system? Why? Because see, even though this force is doing some kind of work, is this force causing a torque about this axis, about the axis that is in white? The torque due to this force F is nothing but 0. Okay, so there is no torque acting on the system about this axis 1. So can I apply conservation of angular momentum? Obviously. So first equation is conservation of angular momentum. Conservation of angular momentum. Angular momentum. Okay. So in conservation of angular momentum, see, if I say, okay, so from conservation of angular momentum, I can easily say something like this. Okay, initial angular momentum of the system with omega naught is equals to final angular momentum. That means when this ball reaches to the center, the disk or the entire system would rotate with some other angular velocity. Okay, and initial angular momentum of the system is equal to final angular momentum of the system, and we get the value of final angular velocity of the system. Okay, so when the ball is somewhat like this, okay, when the ball is, see, this is a disk. Okay, just a minute. Okay, this is a disk, and the ball is the center of the disk. Okay, and when the ball is the center of the disk, now the disk would be rotating with some other angular velocity omega. Okay, the thread is still pulling it, but this force to the thread is not causing any torque on the system. So what is the initial angular momentum? Moment of inertia of the disk. Moment of inertia of the disk is nothing but m r square by 2 plus moment of inertia of the small mass m over this axis is nothing but m into r square, isn't it? Plus m r square. into omega naught is equals to final angular momentum. What is the final angular momentum? Moment of inertia of the disk, which is nothing but m square by 2. M square by 2. And what is the moment of inertia of this small mass that is at the center? M into 0 square. Okay. So I into omega. So I omega initial is equals to I into omega final. This initial moment of inertia into initial angular velocity is equals to final moment of inertia into final angular velocity. Okay. And from this equation, I can simply find out the value of omega. So omega is equals to m square by 2, or let me take r square common. Okay. So if I take r square common, r square into m by 2 plus m divided by m r square divided by m r square by 2, okay, into omega naught, or r square will get cancelled. So we left with, or omega is equals to how much? 2 by m into m by 2 plus m into omega naught. Okay, so this is a simplified answer if I solve this one. Now the final part of the question: what is the work performed by force? See, there is no way you can find out the work performed by this force until and unless you know the value of force. But there's a clever workaround out here. Okay, if I apply work energy theorem in this case, what are the forces that is doing any kind of work? Yeah, see, since this is a horizontal table, okay, the horizontal table gravity force is doing invisible work. The only forces that is doing any kind of work is nothing but the tension forces, isn't it? So the work done by tension force is nothing but the work done by force F. And what is the work done by force F? Change in kinetic energy of the system. So if I apply work energy theorem, we say that change in kinetic energy of the system is equals to work done by all the force, I'll get my answer. Okay, so I'm doing my next part of the question out here. Applying work energy theorem. Applying work energy theorem. What does work energy theorem say? Simply final kinetic energy. What is final kinetic energy? This is the final state and this is the initial state. Final moment of inertia is nothing but this one. This one is the initial moment of inertia. So half I into omega square, okay, minus half I into omega naught square is equals to how much? Work done by force. Okay, so if I apply out here half I final, what is the value of I final? The value of I final is nothing but m r square by 2. This is the final moment of inertia, no? So m r square by 2 into omega. What was the value of omega? We just obtained it right now. 2 by m into m by 2 plus m omega naught square. So 2 by m, 2 by capital M, okay, into m by 2 plus m into omega naught whole square, okay, minus I, this is the initial moment of inertia, into omega naught square. So minus, let's say, so minus half, what is the initial moment of inertia? This one, m square by 2 plus m square. So m r square by 2 plus m r square into omega naught square is equals to work done by external force. Now if I just simplify this one, I'll get my answer. Okay, so let me just quickly simplify this one, okay, without any further ado. So what are the things that I can take common? Okay, so before simplifying this one, let's just multiply. See, this 2 by m and m by 2 will get multiplied to be 1, and it will be 2m plus small m. So this entire thing, okay, this entire thing would be nothing but 1 plus 2m by capital M. Understood? So if I substitute this entire thing, okay, it would be nothing but 1 plus 2m by capital M. Understood? Into omega naught square. Okay, fair and fine. Now what are the remaining things that I can do? See, I can take half common, and what are the things that I can take common? I can take half and r square, omega naught square common. Okay, so I'm taking half common, half is taken as common. Okay, half. Okay, I can take r square also common, r square common, r square common, r square common. Okay, so half r square into omega naught square. I can take omega naught square common, omega naught square common. Okay, so half r square omega naught square. Now what I'm left with is m by 2 into 1 plus 2m by capital M whole square minus m by 2 plus m. Okay. Now if we just simplify this algebraic operation, we'll get the value of this what we call. We'll get the value of the work done by friction, means work done by external force M. So how does simplify it? Just explain this one. Okay. So half r square omega naught square. Do it faster than me. Okay. This is a challenge. M by 2 into 1 plus 4m square by m square. Okay. Plus 2 into 2ab. 2 into this. So 4m by m. Okay. Minus m by 2 minus m. Okay. Is equals to work done by force. Okay. What are the things that I can cancel out here? Minus m minus m. There's nothing I think I can cancel out here. This is a cubic m cube, cubic root. Okay, let's multiply it by 2. Okay, so half r square omega naught square into m by 2. So m by 2 plus 4m square divided by m square. If I multiply this by m by 2, so out here square would get cancelled. Okay, square would get cancelled and 4 would get cancelled to become 2. Okay, plus 4m by m. Out here m would get cancelled and it would be 2m minus m by 2 into m by 2. So it is nothing but minus m square by 4 minus m into m by 2. So this is our work done by external force F. Okay. And is there any other can any more simplification be done? Obviously it can be done, but leave it at this only. Okay. So this is our net force. Understood? So this kind of problem you have done previously in your classes. Okay. So what this problem says that there is a mass M2, disk of mass M2. Okay. And there is a man of mass M1. Okay. And this mass M1, okay, starts moving in the disk at the edge of the disk. So when the man has moved by an angle theta dash with respect to the disk, okay, with respect to the disk, what is the angular displacement of the disk in opposite direction? This is the basic question. And this question you have done in HCV. This question is repeated. You have had exposure to this kind of problems. Okay. So my first question is, what is the equation that I'm going to apply out here? I'm simply going to apply conservation of angular momentum. Okay. So see, what is the initial angular momentum when everything was static? When everything was static, the initial angular momentum was 0. If the person starts moving, his feet experience or his feet applies a friction force on the disk, equal and opposite reaction force applies on him. Okay, but those are internal forces, no? So there are no external forces or torque getting applied on the system. So the conservation of momentum can be applied out here. Initial momentum of the system was 0 when the person has moved through an angle distance, let's say phi dash, left with this, the final angular momentum of the system will also be 0. And while in the process of motion, the angular momentum of the system was also 0. So what I'm going to apply out here is conservation of angular momentum. Now say I'm seeing this disk, okay, seeing this disk from the top view. Okay, this disk was kept horizontal plane, and I'm seeing from the top view like this. So this is the disk of mass M2, and the person has moved distance M1. Okay, of phi related to the disk, phi dash. Okay. Now my first question is, whenever you apply conservation of momentum or conservation of angular momentum, all your velocities must be from the same frame of reference. That means you cannot apply velocity 1 from ground frame, velocity 2 from moving frame. Okay. And wherever you're applying your conservation of momentum from, make sure there is no external force on the system, such as pseudo force or those kind of force. Okay. So this theta dash or phi dash is from frame of reference of disk. Okay. So displacement of man with reference to disk, with related to disk, is nothing but displacement of man related to ground minus displacement of disk itself. This is the core concept of relative motion. Velocity of wave with respect to b is nothing but velocity of wave minus velocity of b. Okay. Now see, the thing I'm going to apply is conservation of angular momentum. Conservation of angular momentum. Angular momentum. I'm going to apply the fundamentals of conservation of angular momentum. See, if the angular momentum of the system was 0 through the entire process, the angular displacement of the system, not angular displacement of individual bodies, the angular displacement of the entire system throughout the entire motion would be 0, isn't it? Since the angular momentum of the system is 0. The angular displacement of system is also 0. That means just forget linear movement, angular things for a little bit. Just focus on linear. If the linear momentum of the system is 0 throughout the motion, okay, the angular displacement of center of mass is what? 0. Same kind of logic we're applying out here. Okay. So what is angular displacement of the system? Same thing. Moment of inertia of disk m2 into r square by 2 into displacement of the disk. Okay. Plus moment of inertia of the man m1 r square into angular displacement of the man. Angular displacement of the man with reference to ground. Okay. All my velocities must be from same frame of reference. So plus displacement of disk is equals to angular displacement of the man with reference to ground. So I must apply this value, not this value. Okay. So m r square is nothing but phi dash plus phi d is equals to initial angular displacement, which is nothing but 0. Now if I solve for if I solve for what I'm solving for theta d, phi d, or angular displacement of the disk, I'll get the value of that one. Okay. So let me isolate my term. Okay. How do I isolate it? m2 r square by 2 phi d plus m1 r square into phi dash plus m1 r square into phi d is equals to 0. Okay. And after that, what do? After that, isolate the thing that I'm going to find out. Phi d common. Let me take phi d common. Okay. Phi d common is nothing but m2 r square by 2 plus m1 r square. Okay. And let me take this phi dash terms to the right hand side is equals to minus m1 r square phi. Okay. I can cancel out the r square. Take r square common out here and cancel out the r square out here. So phi d is nothing but minus m1 phi divided by m1 divided by m2 by 2 plus m1. This is nothing but remains from the r square. Okay. So this would be nothing but minus, if I take LCM out, it would be m2 plus 2m1, and this 2 would be gone up here. Okay. Minus 2m1 phi divided by m2 plus 2m1. And this minus signifies out here, if the person moved in this direction, the angular displacement of the disk would be in opposite direction. Okay. So this was the crux of our question. Now the second part of the question is asking the force moment related to the rotation axis with which the man is acting on the disk in the process of motion. That means while the man is moving, his feet is exerting a friction force on the disk that is making a disk moving anti-clockwise direction. If the velocity is given by this one, the velocity of the man varies as this one. We have to find out the force, okay, with which the man acted on the disk. So simply we can apply, see, instead of going further or instead of further complicated, I forgot to apply dash out here. Okay, see, this dash that I given out here. I forgot it out here when I shifted this side. Okay, so don't make those kind of silly mistakes. Okay. Now the second part of the question is asking the force moment related to the rotation axis with which the man acted on the disk in the process of motion. That means while the man is in motion, okay, while the man is moving, his foot is applying a friction force on the disk, no? Okay, and we have to find out the value of that force moment. Force moment means we have to find out the value of torque generated due to the friction force. Okay, given that the velocity of the man varies at time v dash t. Okay, okay. So out here, torque on the disk is nothing but moment of inertia into angular acceleration of the disk. Okay, so moment of inertia of the disk is nothing but mass of the disk into r square by 2. What is the angular acceleration of the disk? The angular acceleration of the disk is nothing but d square displacement of the disk divided by dt square. Isn't it? Understood this much? Okay. And what was displacement of the disk? Displacement of the disk was nothing but this value, isn't it? This is the displacement of the disk that I found out, no? Angular displacement of the disk. So I'll get is equals to d square by dt square into minus 2m1 by m2 plus 2m1 into phi dash. Okay, or angular displacement. This is nothing but angular displacement of the man related to the this phi dash. Okay. Now let me take all the constant term outside. This minus 2m1 divided by m2 plus 2m1 is a constant term, no? So let me take it outside. It is nothing but minus 2m1 divided by m2 plus 2m1 into d square phi by dt square. Okay. And in the given question, okay, v dash t. What was v dash t? It is nothing but d omega, or not d omega. It is nothing but omega dash. What is omega dash? Omega dash is nothing but velocity of the, or angular velocity of the man with respect to this into r, isn't it? So omega dash is nothing but v dash t by r. And what is omega dash? Is nothing but d phi dash, or relative displacement of the man with respect to disks. Okay, is equals to v dash t divided by r. Okay, now if I just substitute this term with this term, I'll get my answer. So this is nothing but minus 2m1 divided by m2 plus 2m1 is equals to d by dt square, sorry, d by dt into d phi dash by d phi dash by dt. And what is d phi dash by dt? Is v dash t by r, that is given in the question. But this is nothing but v dash t by r. V dash t by r. Okay. And if I take the entire thing, torque applied on the disc due to the friction force by the foot of the man is nothing but m2 r square by 2 into minus 2m1 divided by m2 plus 2m1 into v dash, or v dash t by dt into r. Now this r and r square will be cancelled. These two and these two will get cancelled. So what you are left with? You are left with nothing but this term. Torque applied on the disc is nothing but m2, or minus just signifies the direction. Okay, minus m1 m2 r divided by m2 plus 2m1 into dv dash by dt. Okay, so this was the question. Understood this much? Now this question also you have done. Okay, there is one disk rotating with angular velocity omega 1 of moment of inertia I1. There is another disk of moment of inertia I2 rotating with another angular velocity omega 2. When these two disks are placed together, they'll start rotating with common angular velocity. We have to find out the common angular velocity. Okay, I can simply apply conservation of angular momentum. So this portion you're relatively familiar with. Okay, I'll still do that. Okay, so one of the disk of moment of inertia I1 that is rotating with angular velocity c. This is the axis of rotation. Okay, it is rotating with omega 1. Another disk is I2 rotating angular velocity omega 2. Okay, and when these two disks are put together, okay, 1 and below 1 2, they start rotating with common angular velocity. We have to find out the common angular velocity. So conservation of angular momentum, conservation of angular momentum, angular momentum. Okay, so in conservation of angular momentum, I'll simply apply initial angular momentum I1 omega 1 plus I2 omega 2 is equals to I1 plus I2 into omega 2. So final angular velocity, or common angular velocity after stabilization, or after both the disk moves with same angular velocity, I2 omega 2 divided by I1 plus I2. So this first part of the question you are more or less familiar with. What happens in the second part of that is, see, while both the disks are adjusting to the same common velocity, okay, one is getting decelerated, the other one is getting accelerated, and which torque is doing that thing? That is nothing but when both the disks are compressed, the friction torque is doing that thing. Now my question is, what is the work done by that friction torque? I can simply apply conservation of, not conservation, work energy theorem of it. Change in kinetic energy of the system is equals to work done by all the forces acting on the system, or all the forces, or all the torque acting on the system. So there is only one torque acting on the system, and that is nothing but the friction torque. So not conservation, work energy theory. Okay, so change in kinetic energy is equals to work done by all the forces or torque. What is final kinetic energy? This is I1, this is I2. So half I1 plus I2 into omega. What is initial kinetic energy? Half I1 omega 1 square plus half I2 omega 2 square. So half I1 omega 1 square plus half I2 omega 2 square, okay, is equals to work done by friction force. Understood? Okay. So, okay, half I1 plus I2 into what is the value of omega? The value of omega is nothing but this term. So, this square. I1 omega 1 plus I2 omega 2 divided by I1 plus I2 whole square minus half I1 omega 1 square plus minus, if I open the bracket, it will be minus half I2 omega 2 square is equals to work done by friction. Okay, now all my focus will be on simplifying this equation. This entire denominator term will be I1 plus I2 whole square. Okay, so let me erase this entire term. That would get cancelled with this term and would only be remaining nothing but I1 plus I2 at the denominator. I1 plus I2 at the denominator. Okay, then fine. Now, is there anything else that I can do? I1 square omega 1 square? No. So I'll leave the equation as it is. Okay. So this will be our final form of the equation. If you want to simplify it more, what can you do? You can take I half omega common and then take the term. Okay. But I don't think there is any more use of simplification, because ultimately what we'll be doing is this I1 square omega 1 square. If you take the denominator common, I1 plus I2 common, we'll be multiplying with this term. Okay, I1 omega 1 square, I2 omega 1 square, and somehow addition subtraction. Okay. So let me leave the term as it is. Okay. And if there are values given, directly substitute the values in this form only. There is no need to further, break down. Or if you want to break down the simplification, you can take half common. Okay, LCM is nothing but I1 plus I2. Let me do one. I1 square omega 1 square plus I2 square omega 2 square on this term. Okay, and if this is the LCM, I have to multiply the LCM by these two terms. Okay, so it will be nothing but minus I1 square omega 1 square. Okay, minus I2 I1 omega 1 square, and again minus I2 omega 2 square, I2 square omega 2 square, minus I2 I1 omega 2 square. And what will get cancelled? I1 omega 1 square and I1 omega 1 square. I2 omega 2 square and I2 omega 2 square is getting cancelled. So let's cancel out this term. Okay, cancel out this term, cancel out this term. Okay, let's make it neat and clean. Let's bring this term out here. Okay, and this is nothing but the cancellation term. Let's bring this term also out. Okay, let me close the bracket and let's this one. Let me take the minus common out. If I take minus common, it will become plus out. Okay, so minus. Okay, so it will be this one. Okay, and I'm not, there's no point of further any simplification. Work done by friction. Okay, work done by friction is nothing but negative. So this is our question.